This is Physics Lab 5, Choose Your Own Adventure. In this lab, we will be observing the motion of a slinky through gravity. We will explain the physics of its motion through VPython and Tracker. The following video is now the motion we would like to analyze. Pay attention to how the slinky behaves in regards to gravity with the tip and bottom portion of the slinky moving separately. Watching the video, I decided to try this out myself and collected data with Tracker with my own slinky. I used 2 point masses, one for the top portion and one for the bottom portion. Principles we will use in this lab are fairly simple, which include the tension force and gravity acting on the bottom portion, while only gravity works on the top portion. The key to this motion is the time it takes for the slinky to become compressed and the instant the bottom portion realizes the lack of a tension force. We will now create a VPython model of the motion we observed. The initial conditions of the slinky are seen here. The key to this model is to break it into parts of the top and bottom of the slinky as 2 masses. We will make 2 spheres, one to represent the motion of the top and one to show the bottom portion of the slinky. Realistically, there will be multiple balls for each coil to show the true motion, but this is a fairly simplified model. We now put in the physics in VPython. The different forces are seen here, with the top slinky being under the influence of only gravity under the time frame. The time frame for when the top of the slinky hits the bottom portion is seen in the next portion of the code. Notice how the highlighted portion of the code signifies a tension force acting on the bottom. We even include drag force for both portions with a constant to better replicate the motion. We finally then use Newton's second law for both the top and bottom portions to update their positions and velocity. Now we run the code. Unfortunately, like the video, the code is unable to realize the relapse time between the force of tension dissolving, which is why the top portion and bottom portion move at the same speed. The tension force that is supposed to keep the bottom portion of the slinky unmoving is not seen by VPython. However, the entire motion of the slinky as a point particle system is still correct, and the data from these 2 graphs show it. The VPython and Tracker data are similar as the entirety of the motion is identical. The discrepancies can be seen due to an approximation of the drag force. We then look at only the bottom portion of the slinky independently and see how it is unmoving for a period of time before it falls, as the tension force counteracts gravity for the period of time. The interesting part of this motion is how the lack of a tension force is instantaneous and the bottom portion is completely motionless until the top portion completely compresses. Now, what if questions? What if the slinky was a mile long and dropped from an extremely high altitude of at least 5 miles? Would the bottom of the slinky still behave the same way? No, the key is seen in the time it takes from the bottom of the slinky to realize its lack of tension force. The slinky would have too much time to realize its tension force getting smaller, and it would start to drop before it fully compressed. What if a weight is attached to the bottom of the slinky? Would it still behave the same way? Yes, the slinky will still hold the same tension force and gravitational force that held it in place the first time, as tension force completely is there to counteract weight force and is identical with different direction. The slinky would still compress, with the bottom portion still being motionless and intact. Further analysis of the slinky can show how the kinetic and potential energies are separate for the bottom and top portions. However, no matter the case, the physics will always stand true and show how the forces act even on counterintuitive models such as this one. Thank you for watching.